Hello students, today I am going to teach you all motion in a straight line. This is the second lesson of your grade 10 science textbook. As you all know, this lesson is a physics lesson. Okay, if we come back to the topic, motion in a straight line, there are two components to this topic. First part is the motion. Now, if you think about examples for motion, you see this every day in your day-to-day activities. A person walking, a child running, a fan rotating, a fruit falling from a tree. These are all what you see around you all. At the same time, if you take the solar system, the earth rotates itself around its axis. All the planets go around the sun, they revolute around the sun. Now, these are all different types of motions. If you look at them carefully, you can divide them into two main types. If you think of the fan, it rotates around its axis. The earth rotates around its axis. The planets go around the sun. So here we use the term around. So there you can imagine that it has a motion related to a circular path. We are not going to worry about those types of motion under this lesson. We are going to discuss straight line. The other examples, a fruit falling from a tree. From the top of the tree, it comes down. It has a certain direction. The tree is the starting point of the fruit and the ground where it falls is the end place of the fruit. So, there is a start point and a destination. And this occurs in a certain direction. When you walk, you start from one place, you have a destination where you want to reach. So, there also you use a straight path in a certain direction. So, the different types of motions that come under the motion in a straight line usually occur in a certain direction and in a certain straight line path. So, with this in mind, we'll look at what we will be discussing under this lesson. Vector and scalar quantities, distance and displacement, speed and velocity, acceleration and deceleration, displacement time graphs, velocity time graphs, and gravitational acceleration. So, as we enter the lesson, we will first discuss about vector and scalar quantities. Now, from this, if we talk about quantities, you will have experience going to a shop to buy something. You don't ask for, give me some sugar. Instead, you ask, give me 500 grams of sugar or 1 kilogram of rice. The same way, when you fall sick, you just keep your hand on your forehead and feel that you have a temperature. But when you go to the doctor will want to take your temperature reading. So, as you all can see, these are quantities which can have a qualitative value, high, less, medium. But still, for a calculation to be done, the quantities have to be measured using an instrument. In that sense, we will measure the amount of substance in mass. This has a unit, kilogram, grams, and etc. Same way, we measure the temperature of a sick person using degrees Celsius or Kelvin using the instrument thermometer. As you all know, when we travel on the road, the vehicles have to maintain a certain speed limit. Speed for one person might be slow for another person. So, in order to maintain a proper limit and to have a proper idea as to what speed or how fast you are traveling in, we use this particular meter, which is called a speedometer. This indicates how fast we are traveling in a vehicle. The last example that is commonly used for practicals or activities in the laboratory to measure time. 2 minutes, 5 minutes for this reaction to change or this change to occur, or when athletes practice their events, time themselves how fast they can run based on this instrument. You all know the name of this instrument. It is called a stopwatch. So as you all can see, these are all different types of quantities. And these quantities are measured using an instrument. Therefore, these quantities have a magnitude. They have a magnitude. But if you look at all four quantities, they don't have a direction. We don't talk about mass in a certain direction. Temperature doesn't have a direction. Speed, whether the car moves from your right to left or left to right or forward or backward, doesn't matter. It only has a magnitude. The same way, time does not have a direction. So, all these four quantities do not have direction. They don't have direction. So, they have a magnitude, but they do not have a direction. These types of quantities are given the name scalar quantities. So remember children, any quantity that can be measured, it has to be a physical quantity that only has a magnitude but does not have a direction is called a scalar quantity. So we will see what vector quantities are. Now look at this example. There is a bag of candy on the table. Now you and your friend want to share this bag of candy. So first your friend pulls the bag towards himself. When we say pull, you all know pull or a push is a force. So this is a quantity. So let's say your friend applies 5 Newton force to pull the bag towards himself. After he takes his share, what happens when he pulls it? The bag moves from here towards this direction. Once he has taken his share, you want to take the candy from the bag. So you pull it towards yourself on the other side, towards the other side with the same amount of force, 5 Newton. So then the bag moves towards you. Earlier when your friend pulled the bag, it went towards the west direction. Then now it moved towards you, that is the east direction. So here we applied a force with a certain magnitude, that is the 5 Newton value, and depending on the value and the direction, the object moved. So this is a quantity force which has a magnitude and a force and a direction. A magnitude and a direction. So the second type of quantity has a magnitude and direction. Then we call this as a vector quantity. Now let's look at the second example. Now there are two aircrafts. We'll say this is the first one and this is the second one. Now the first aircraft wants to attack the second aircraft. So there are two things that should be considered by the pilot. He should know how fast this second aircraft is going, so he can go faster than that and catch up with this second aircraft. At the same time, if he just maintains the normal direction, his own direction, then of course he will go in a different path. So therefore, the first aircraft should know in which direction he has to move. So he has to go in this direction towards the second aircraft with a speed more than the second aircraft. So here he needs to consider the magnitude, the value, the rate at which the second aircraft is moving and the direction in which the second aircraft is moving. So therefore, this is a second quantity which we will be discussing in detail afterwards, which is called velocity, that has a magnitude and direction. Therefore, this comes under vector quantity. So I hope you all got a basic idea about what scalar quantities and vector quantities are. So we will see whether we are able to classify quantities under these two types. There are some examples given to you. So from these, we will need to select what is vector quantity and what is scalar quantity. I will use a circle to denote the scalar quantity and I will use a star to denote the vector quantity. So as we discussed before, mass does not have a direction, it has a magnitude, therefore it comes as a scalar quantity. I will use a different color as well. So for mass, it is a scalar quantity. Time, as you all know, does not have a direction, therefore it is a scalar quantity. But as we discussed before, force has a magnitude and a direction. So therefore, this is a vector quantity. Now these are two new things, distance and displacement. Distance is just the length. Now when in a march past, when they tell you to take one hand distance, you put one hand forward, the other hand towards your side. There you are not considering the direction. It's only the length between you and the person next to you on either side and the person in front and the person behind you. So here we only consider the length, that is only the magnitude. Therefore, distance is a scalar quantity. Then we talked about speed. It shows you how fast an object is traveling, not the direction. So therefore, that again is a scalar quantity. As we discussed before, temperature does not have a direction. So that is also a scalar quantity. But like the aircrafts, you need to consider the magnitude and the direction when we talk about velocity. So therefore, it is a vector quantity. And finally, the displacement. Displacement again talks about magnitude in a certain direction. Movement in a certain direction. So this has a magnitude and a direction. Therefore, this is also a vector quantity. So as you all can see, to summarize, mass, time, distance Speed and temperature are scalar quantities. Force, velocity and displacement are vector quantities. So I hope you all have got a good understanding about what scalar quantities and vector quantities are. With that in mind, we will see how we will be defining these two quantities. So for an exam, if they tell you to define scalar quantities, you will have to write this definition. A physical quantity which can be described only by its magnitude is called a scalar quantity. So you have to say physical quantity, that is a measurable quantity, and magnitude only. And the examples are speed, mass, time and distance. Similarly, we can define vector quantities also. So again, a physical quantity which can be described by its magnitude and direction is called a vector quantity. So here again, a physical quantity, it has a magnitude and a direction. So this is called a vector quantity. And the examples are displacement, acceleration, velocity and weight. With these considerations, we will now see what distance and displacement are. Okay, the first topic, distance and displacement. We will see what distance and displacement are. So here, as you can see in this diagram, there is a child who wants to start from point A. So this will be her starting point. And she wants to go to another place which is point B. And that will be her destination. Now this child has many options. There are 3 different paths. Path P, path Q, path R. And the child can take whatever path she wishes to travel through. You all will have experience in school when you want to go from one classroom to another. If you want to go fast, to go to a place where you like something that is taking place, you choose the shortest path. But if you want to spend a lot of time walking with your friends, then what do? You choose the longest path from the first place to the second place. So here we'll see what the child will do. If she prefers to take path P, the length of the path is given to you. It's 320 meters. So when an object or a person travels from one point to the other, they use a certain path and the total length of the path taken to get from one point to another will be called the distance. So here you can see it's only the total length. So if we compare the 3 paths, path P has a length of 320 meters. So we say the distance is 320 meters. If we take path Q, the distance is 200 meters. And path R has a distance of 240 meters. Now, if you see, all the paths start from point A and end up at point B. But only difference is in path P, you can see the first move is towards this side. And it goes in a certain design, right, where the direction of the path changes. So we will not be considering the direction for this path. If the child takes path R, she will be moving towards this direction, which is the opposite of the path P. So when we consider the distance, we will not be considering the direction. So distance only has a magnitude, the different values. So distance is a scalar quantity. But whatever the path the child takes, her initial position is A and the final destination is B. So always there is a change in the position of the child from A to B. So this takes place in a direction from A to B. And if we measure the length from point A to point B, it is different. It has a magnitude of 160 meters. And when we compare, you can see out of all these paths, this is a path that is a straight line, and that is the path that has the shortest distance, and it has a direction from A to B. So therefore, we call this change in position as displacement. So if we define displacement, it is a change of position that occurs from one point to another point in a particular direction. So here we talk about change of position in a particular direction. Then we will be writing this as 160 meters from A to B. And this magnitude 160 meters is the length of the shortest path in a straight line. So if you draw the straight line path, the shortest will be the displacement, and it will have a direction. So this is the difference between distance and displacement. Keeping that in mind, we will look at examples as to understand distance and displacement in more detail. So this is example 1. Black color arrow in the figure shows the path taken by a child to travel from home to school. So here you can see this is the home. So that will be the start. And this is the school, which will be the end point or the destination of the child. So as shown in the diagram, you can see the child starts from home, that is point A. She travels towards point B in this direction, then takes a turn, travels towards point C. And here also you can see the length of the paths are different. A to B is 100 meters, B to C is 400 meters, and finally in this direction C to D is 200 meters. But when we talk about the distance traversed by the person or the child, we only consider the length. So here we will have to adapt the length from A to B, B to C, and finally C to D. That will be equal to 100 meters plus 400 meters and plus 200 meters. Always children, when you write values with a unit, it would be better if you substitute with the unit itself, so that you will never forget to write the unit with your answer. So if we add them together, you will get a value of 700 meters. So that is the distance traversed by the child to go from home to school. But if we take the displacement, it is the shortest, the magnitude is the shortest distance, and it has a direction. So this depends only at the starting point and the end point. So here the displacement is from A to B in this particular direction. Here remember children, when they give you a direction and say, okay, this is the north or this is the east, then when you write the displacement, we specify that particular direction. Otherwise, even though you have a knowledge about directions, don't just look at the diagram and determine the direction for the displacement. Instead, there is an easy way. We look at the points, the starting point A and end point D. So, we will use them for our direction purpose. And also, here they have marked the length of this path, that is the shortest distance, that is 500 meters. 500 meters, the direction will be from A to D. So as you all can see, the child started from home and went to school. The distance traversed by the child is 700 meters, but the displacement of the child is 500 meters from A to D. So there is a difference between the distance and the displacement, although the motion was the same. Okay, we will look at the next example. Okay. Example 2. A child starts from point A and reaches the point B along the path indicated by the arrows. So here you can see initial point is A and the final point is B. It's shown to you in the figure. And the path taken by the child, there is only one path and the distance is given as 400 meters. So there is no calculation for y'all. You know the distance traversed by the child is 400 meters. We only write the magnitude for this. But here you can see the displacement is from A to B. This has a magnitude of 120 meters. So that is shorter than distance. So we write it as 120 meters. That is the magnitude. Now we have to specify the direction. Again here they have not given us a direction as to which is the north or east or west. So we will only depend on the initial point and the final point. So therefore we will say displacement 120 meters from A to B. Again you can see the magnitudes are different and there is a direction for displacement. So this is where for the same person undergoing the same motion, the distance and the displacement are different. We will look at another example. Okay, this is something familiar to you all. In school, you have your running events and you all use a running track to do this event. Here they have shown a 200 meter running track used in track events is shown in figure. So as you all know, the tracks are usually oval in shape and you have different types of running events. You might have to cover one round or two rounds or sometimes 1.5 rounds or half or quarter round or part of the track needs to be used for a certain event. So as we can see, for a 200 meter running event, the athlete has to start from this point A and has to go and finish at point B, that is here. And in this running event, the athlete has to go this way, take a turn and again go in another direction. So it's from A to X and thereafter X to B. So this path has a change in direction. If we just look at the distance of the running track, they have said it is a 200-meter running track and the length has been shown to you. This is 200 meters. So here, if you look at the second diagram, it is even more clear. This red arrow indicates the track, which is 200 meters in length. So the distance will be 200 meters. But when the person is running, when the athlete is running, they will start from point A, move towards north and then take a turn and move towards the west and finally reach point B. So here there is a change in direction and also as you can see the angle in which the direction change occurs has been given to you as 70 degrees. So therefore, when we mention the displacement of the athlete, we have to take the magnitude and the direction. If we look at the diagram, the magnitude is marked for you 160 meters. So here the displacement we will write as 160 meters. We have an angle. So for the direction, we will say 70 degrees from north to west. So it is the displacement 160 meters, 70 degrees from north to west. That is the displacement of the person. Another example where we look at the motion of a car. As you all know, there are different types of cars. One can be a short one, there can be a longer car. So it will be difficult when you have more than one cars to compare them if you consider the full length of the car. So therefore, we always take the midpoint of the car to consider its position. So as you can see in this diagram, the midpoint of car is in the 0 position or the starting point A. So in the first diagram, the car is ready to start its motion. It's in its initial position. Therefore, there is no distance traversed or no displacement. Then for this first instance, we write the distance as 0 and the displacement as 0. That is the initial position. If you go to the second diagram, from this, the car has moved this way from A to B and reached the point where the length is 4 meters. So therefore, the car has travelled a distance of 4 meters. If you consider the displacement, it is from A to B 4 meters. The same length from A to B. This is the second position. Now we go on to the third position. The car travels from A to B and from here B to C. Now this point, the midpoint of the car is along with the 3 meter mark. So the distance travelled from B to C is 3 meters. But if you consider the full movement of the car, Initially it traveled from 4 meters A to B and then 3 meters B to C. So if we consider the total distance, we will be taking the total distance A to B plus B to C. So that will be 4 meters plus 3 meters, that is 7 meters. Now if you look at the displacement, we need to consider the initial position and the final position. Initial position is A and the final position is C. So if we use a line to indicate the initial and final positions of the car, it is from A to C and it is in this direction. Now we don't know the length of this shortest distance. We do not have the measurement. Then we will have to do a calculation. So we will see how we can calculate the displacement, the magnitude of the displacement. Okay. From this, if you look at the shape of the path traveled by the car, you can see it looks like a triangle. A triangle like this with this particular angle, which is a 90 degrees angle. And you know, a triangle that has a 90 degrees angle is called a right angle triangle. Now you will remember the relationship between the lengths of this triangle. This is given by the Pythagoras theorem. Pythagorean theorem or the Pythagoras theorem, which says from here, this is AB and C. So AC is the right angle. So the theorem says AC squared will be equal to AB squared plus BC squared. So we already know the values of AB and BC. So that will be 4 squared plus 3 squared. 16 plus 9, which will be equal to 25. To find the value of AC, we take the square root of 25, that will be 5. So the length of AC will be 5 meters. So the magnitude of the displacement is 5 meters and the direction will be from A to C. So here we write as A to C. So remember students, when you are given a diagram like this, look for a triangle which has a 90 degrees angle and apply the Pythagorean theorem and you can find the length of the displacement. That will be the magnitude and you will know the direction. So as you all see here again, for the movement of the car, the distance and the displacement values are different. We will look at another example. Example 5. Now consider a situation where a child is walking 60 meters from A to B. 60 meters from A to B. Always when you read a question, it would be better if you can write down the data given to you. In case they do not give a diagram like this, it would be better if you practice writing down the data first before you do the calculation. So here everything is shown to you in this diagram. The child starts from point A, walk towards this side, and here they have shown straight line path as shown in figure. They have not mentioned the direction. So we will have to consider the direction as A to B. 60 meters from A to B. Therefore, the distance will be a direct value 60 meters. But the displacement, again with the magnitude 60 meters and the direction from A to B. So here you can see, since it's a straight line path from one point to the other, that is the shortest distance. Therefore, the distance and displacements are same in their magnitudes. But displacement has a direction. We will see what the child does next. Now the child walks another 40 meters along the same direction, another 40 meters. So already she has covered from A to B. Now from B to C in the same direction. So therefore the distance will be from A to B plus B to C. So if they tell you to find the distance traversed by the child A to B plus B to C, that is 60 meters plus 40 meters equals to 100 meters. The child has travelled a distance of 100 meters. If you take the displacement, again it's a straight line path and it is in the direction from A to C now. So the magnitude will be the same, 100 meters, and the direction will be A to C. So here we adapt the distances, same magnitude, direction is A to C. We will see what happens next. Now the child decides to walk back. Now suppose that the child walks back 40 meters after reaching point B. Initially, the previous example, the child walked further in the same direction, but now the child wanted to walk backwards. So now if we calculate the distance, you can see the child walked from A to B, that is 60 meters, but again turned back and walked from B to C, that is 40 meters. A to B, B to C. This is equal to 60 meters plus 40 meters, that will be 100 meters. Here no problem, no direction, therefore you just adapt the values. But for the displacement, if you look at it, you have to consider the starting point A, that is the start, and this is the end point or destination. So the change in position, initial position, final position. So that is the displacement. We will be considering from point A to point C. We know the full distance 60 meters. We know this distance 40 meters. So the length of A to C will be the difference in the two lengths. So we need to subtract BC from AB. AB minus BC will give you the magnitude of the displacement. That will be 60 meters minus 40 meters. So the value will be 20 meters. But here again, The initial position is A and final position is C. So the initial position was point A, the final position is point C. Therefore, we say displacement 20 meters from A to C. So you will only consider the initial and the final positions. As you can see again, the values of the lengths are different, that is the magnitudes are different, and displacement has a direction. Another example where we look at the movement of the car. Now you can see from the first picture, the car is in position A, that is 0, the starting point. So from point A, the car moves towards this direction A to B, point where the distance is, we will take it as meters. So from 0 to 5 meters, there is a movement in the car. Therefore, if we can find the distance traversed by the car, it will be equal to 5 meters, only the magnitude. But if we look at the displacement of the car, again it's going to be 5 meters in magnitude, but the direction will be A to B. Always remember to write the direction for displacement. We will see what happens to the car in the next instance. So here the car now started from point A, it went to point B, again it has come back to point A and further travelled towards the opposite direction to point C. So if we again consider the positions, this was position 1, then it went to position 2, again it came back to position 3, and finally position C is the last position. If we consider the distance traversed by the car, it will be from A to B, again from B to A, and then from A to C. So that's going to be 5 meters plus 5 meters. Although this is a negative value, for distance we only consider the magnitude. Therefore, that is also going to be 5 meters. So the car has traversed a total distance of 15 meters. But for the displacement, we will only need the initial position and the final position. And this has a direction. So we will have to consider the sign of the value as well. So from A to C, you can see the displacement will be minus 5 meters. This is going to be from A to C. Or else, since you are denoting the direction and it is opposite of the initial direction A to B, you can write it as 5 meters from A to C. Always remember students, here the minus sign denotes the opposite direction. It is not a negative value, it denotes the opposite direction. So I hope you have understood this example clearly, where a car is going in one direction, turning back, moving to the initial position, and thereafter moving a further distance of 5 meters. When we consider the distance, we just add up all the values. But for the displacement, we consider the initial position A and the final position C. Therefore, the value comes as minus 5 meters and the direction is from A to C. I hope you have understood this clearly. Now we will go to the next section. This is from your textbook. A child starts from point A, walks 40 meters to the east until he reaches another point B. And from point B, he walks 30 meters to the north to reach the point C as shown in figure 2.8. So, as you can see, the starting point is A, he goes to B, and the final point or the destination is C. What is the total distance traversed by the child? So here, if we are to calculate the distance, it is the length of the path that has been traversed by the child. So here, distance will be distance from A to B, then from B to C. So we shall do the calculation. Right. So as you can see in the diagram, from A to B is 40 meters and from B to C is 30 meters. So the distance traversed will be the total 70 meters. So that is the distance traversed by the child. Then what is his displacement? As you all know, displacement depends on the starting point and the ending point, the difference in the position. So here, the distance or the length between A to C, the shortest distance is 50 meters. And here, they have mentioned the directions, initially A to B towards the east and then from B to C towards the north. So, we will be writing the displacement equals 50 meters from east to north. So now you have a better understanding, children. When they do not specify a direction, we use only the letters given to us. When they tell us a direction like this, initial movement was towards the east, then it was towards the north. So we write it as from east to north. So again, you can see the difference in the magnitudes of distance and displacement. So this is the next topic, that is speed. So this is a sign that you come across when you travel along the road in your day-to-day activities or day-to-day life, and you can see there is a value given 100 kilometer per hour. H-1 says it's per hour. And here they say it's maximum 100 value. So that means when you are traveling on the road by vehicle, you have to adhere to the speed limit. You have to maintain a maximum speed so that you can avoid accidents. And this maximum value depends from place to place. If it is a city that has lot of traffic, the maximum might be about 50. But if it is an urban area where there is less traffic, it can be 100. In a speedway, it will be more than 100. So, depending on where you are traveling, there is an indication to your maximum speed. So, we will always have to look at the speedometer that we saw in the earlier slide to look at our speed and always maintain the speed limit. And here the kilometer per hour is the unit of the speed. So this actually states how fast you can travel. It doesn't say in what direction. So as we discussed before, speed is a scalar quantity. With that in mind, we will see how we can define speed and do calculations, and to calculate speed and do calculations thereafter. So as we discussed, students, speed is the distance traversed in a unit time. When an object moves from one point to another, there is a length that it covers, and that is called the distance, and the time taken will give you the speed of the object. So therefore, when we divide distance by time, we get the speed. So this is the equation for speed. We write this as the equation for speed. At the same time, they can ask you to define speed. So remember, students, you have to look at the question properly. It is the same quantity. When they ask you to give the equation, you write it in this form. If they ask you to define speed, then you have to say the distance traversed in a unit time. So that is the definition for speed. Definition for speed. The same quantity, equation and definition. As you know, when an object travels, the distance is given in meters and the time is given in seconds. So therefore, we are dividing distance is given the unit meters and time is specified in seconds. So the unit of speed will be meters per second. And here, children, you have to remember, you have to have a small space between the two units as written or shown here. So this is the normal unit, or what we call the SI unit. Meters per second, standard international unit. And also there is an application. If you take an athlete or a person doing a fast walk, usually they cover only a short distance comparatively. So then their traveling is in seconds, and we can easily calculate the speed in meters per second unit. But if you are traveling from one city to another, say Colombo to Kandy or Galle to Nuwara, then it's a very long distance. Then if you go to say give the speed in meters per second, it will be a complicated value. So therefore, we use the unit kilometer per hour. The distance is very long, so that's expressed in kilometers, and the time duration is also longer. Therefore, we use the unit per hour. So both meters per second and kilometer per hour are units of speed. Depending on the situation, we use meters per second, especially when it is a short distance and the time duration is less. But normally for traveling, we use kilometers per hour. And also the SI unit of speed is meters per second. Then we have something called the mean speed or average speed. Now this is from experience. You will know when you leave to school from home, where if you are traveling by a car or a van, you will know that there are color lights in between. So when you go along the road, you will have to stop at a color light. Then the car has to slow down. Then again when it starts moving, it might have to speed up. And also depending on the traffic, if there is more traffic, the vehicle will go slowly. If there is less traffic, the vehicle will move fast. Then the speed of the vehicle will be changing with time. Then of course, we cannot express speed as the normal speed where we divide distance by time. We go for the mean speed or the average speed. Here we consider the total distance traveled from your home to school, the total distance and the total time duration. Only difference is here we are calculating for each instance. The mean or average speed is calculated for the full journey. So these are the equations and the definition for speed. I hope you all got a good understanding of what speed is so that we can apply this equation to calculate the speed of objects in the questions or examples coming hereafter. So the first example, now children, for y'all, the data related to the movement of the object or the motion of an object will be given in a table form like this. Always the time will be denoted first, and time, the symbol is t and the unit is given in seconds. Distance traversed, the symbol is d and the unit is given in meters. Always you have to remember, we will be usually starting the motion from the beginning. Then of course the time will be 0 and the distance will be 0. That is how we usually start the movement of an object. But we will see later, if it is a moving object, it might be different. But always time is started at 0. Then you can see the time duration is increasing by 1 second. The same time interval changes by 1 second. But the distance traversed is changing gradually. So if I just show this as a diagram, we start from point 0, that is the 0 second. That is the 0 second, and the end of the first second, the car has moved 3 meters. And at the end of the second, it has moved 6 meters. But if you look at each time duration, 0 to 1, 1 to 2, within the first second, the car has moved 3 meters. Within the second, from here to here, that is from 3 to 6. So we will have to always take the difference. This is the final distance. This is the initial distance. So 6 minus 3 is the distance traversed within that second. That is the second. So if we calculate the speed, the first second speed is, here you know the equation. Always speed equals distance over time. So in the first second, the distance is 3 meters divided by 1 second. So that will be 3 meters per second. If we take the second, as I told you, from 3 it has gone to 6. So the distance traversed is again 3 meters and the time duration is 1 second. So that is again 3 meters per second. During the third second, if you are to write the change in the equation itself, you can write it as 9 minus 6 divided by 3 minus 2. That is your time. 9 minus 6, 3 minus 2, that again will be equal to 3 over 1, 3 meters per second. So either you can do it in a line like this and substitute the value, or directly you can calculate the distance and time. Then for the fourth second, 12 minus 9 divided by 4 minus 3. So that again 3 over 1, 3 meters per second. And the last or the fifth second, where the distance traversed is 15. So 15 minus 12 divided by 5 minus 4. So that is again going to be 3 over 1, 3 meters per second. Now here you can see all the values are the same. So that means the speed of the object has not changed during the motion. So therefore we call it as uniform speed or constant speed. Constant means a value that does not change. So here the speed has not changed with time. Therefore we call it uniform or constant speed. At the same time, we can calculate the average speed for this motion. If you remember from the previous equation, I can show it to you all. Mean speed or average speed is the total distance travelled divided by the total time duration. So if we use that equation here, the total distance traversed is from 0 to 18. So it's going to be 18 meters divided by the total time duration is 6 seconds. So here 6 seconds, that is again going to be 3 meters per second. So as you can see, the values of speed or the magnitude of speed at each second and the average speed all have the same value. This is true when it is an object is moving with uniform or constant speed. Okay, we will see what happens if speed of an object changes with time. So here you can see again a table of data is given to you. The time, it changes by 1 second starting from 0. But if you look at the distance traversed, you can either draw it in a diagram or you can just look at the values. You can see from here to here there is a change in distance of 3 meters. But from 3 to 5, you can see there is a change in distance by 2 meters. From the second to the third second, it goes from 5 to 9. So the distance traveled will be 4 meters. 9 to 12, again it's going to be 3 meters. 12 to 16, 4 meters. And finally from 16 to 18, 2 meters. So from the values, you can see that the object has travelled different distances during each time interval. So that means the speed of the object has changed. We will now calculate the speed. For the first second, it is going to be 3 meters. 3 meters divided by 1 second. So it will be 3 meters per second. Second, you can see 2 meters divided by 1 second, 2 meter per second. Then the third second, the distance traversed is 4 meters, again divided by 1 second, 4 meter per second. Then the fourth second, distance is 3 meters divided by 1 second, 3 meters per second. During the fifth second, the object has traveled again 4 meters divided by 1 second. The speed is 4 meters per second. So, according to the distance traversed, the speed also has changed. 3, 2, 4, 3, 1. So, this is not uniform speed, not a uniform speed. Therefore, we can calculate the mean speed or the average speed for this particular object. As you remember, the equation for mean speed, what is it? It is the total distance traversed by an object divided by the total time duration. So here, if we calculate the mean speed, the total distance traversed will be 18 meters divided by full time taken, total time duration 6 seconds. So, if we calculate the value of the speed, it will be 3 meters per second. So, as you can see, throughout the journey, the speed has changed and there is an average speed for the motion of the object. So, this is when the object is not moving with uniform speed. With those in mind, we will look at some more examples. Here again, a road is shown to you all, a long distance road where a car is traveling starting from the initial second, that is 0 seconds, and here the distances are shown to you. At the end of 1 second, you can see the car has reached the 4 meter mark. And at the end of 2 seconds, it has reached the 8 meter mark. 3 seconds, 12 meter mark. 4 seconds, again 16 meter mark. And 5 seconds, 20 meter mark. So, when you look at the values 4, 8, 12, 16 and 20, immediately you can identify that the values are changing by an equal number. So, therefore, you would have guessed by now, this is a uniform speed. We will calculate and see. During the first second, the distance traversed is 4 meters divided by 1 second. So, it is going to be 4 meter per second. During the second second, although it has covered 8 meters, the distance traversed will be 8 minus 4. Final minus initial. So, that divided by 1 second will be again 4 meters divided by 1 second. 4 meters per second during the second second. Then the third second, again 12 minus 8 divided by 1 second. That is also 4 meters divided by 1 second. Speed is 4 meters per second. And the fourth second, 16 minus 12 divided by 1. So, 4 meters divided by 1 second. Again, the speed is 4 meters per second. So, as you can see, all the values are same. So, what do we call this speed? it is uniform speed or constant speed. For this also we can calculate the average speed. Before that, I will calculate the speed for the fifth second. That is the last value over there. 20 minus 16 divided by 1. That again is 4 divided by 1. 4 meters per second. That is also same as the previous values. So, if we calculate the average speed, you can remember it is the total distance traversed divided by the total time duration. So, here it's going to be 20 meters divided by total time is 5 seconds. That is also going to be 4 meters per second. So, from this we can conclude during constant speed, average speed is the same as the speed at any given point. So, all the values are the same. That is when it is a constant or uniform speed. We will go on to the next instance. So, as you all saw, the ball or the blue color sphere started from this point, the starting point, at 0 seconds and moved along this path for 7 seconds and reached its final destination, that is the 20-meter mark. If we look at the motion of the ball, you would have seen it looked different from time to time. So, now we will calculate and confirm what type of motion the ball showed. If we take the first time period from 0 to 4 seconds, that is from here to this mark, you can see the ball has traversed a distance of 8 meters. So, if we fill in the data into this table, the distance traversed is 8 meters and the time taken is 4 seconds. So, if we calculate the speed, you all know distance traversed divided by time taken. So, it will be 8 divided by 4, 2 meters per second. The second instance is from this point to this point where the time changes from 4 seconds to 6 seconds. So, the distance changes from 8 to 12. So, here we have a distance traversed that is equal to 4 meters. Why? 12 minus 8. And the time taken is 2 seconds. Why? 6 minus 4. So, if we calculate the speed, it will be 4 meters divided by 2 seconds. That is going to be 2 meters per second. And finally, from 6 to 7 seconds, the distance has been from 12 to 20. So, there is a distance of 8 meters traversed by the ball. And the time taken is only 1 second. So, therefore, if we calculate the speed, 8 meters divided by 1 second, that will be 8 meters per second. So, here you can see initially the ball moved with the same speed, but towards the end it moved faster. So, the first two values are 2 meters per second and the last value is 8 meters per second. Still, it is not a uniform speed. Not a uniform speed. So, again, we can calculate the mean speed or average speed. That will be the total distance traveled divided by the total time duration. So here the total distance is 20 meters and the total time duration is 7 seconds. So we calculate the distance traversed divided by the time. And when we divide 20 meters by 7 seconds, we get the value as 2.85 meters per second. So here you can see the speed of the object has changed during the travel and therefore the average speed is also different from the values you obtained before. This happens when the object is not moving with constant or uniform speed. And children, you all have to remember that you will have to do calculations where you get whole number values as well as decimal values like this. So with that in mind, we have already calculated mean speed or average speed as the total distance traveled divided by the total time duration. We will look at another example. What is the average speed of a vehicle that traveled 100 kilometers from Colombo to Kandy in 2 hours? So here you can see the distance is 100 kilometers, a long distance, and also the time duration is 2 hours. If you remember, when we discussed the definition and the equation for speed, we saw that there are two different units. One is meters per second when the distance is short and it is a small time duration. But here a long distance and long time duration. Therefore, we can calculate the speed in a different unit where we substitute for distance. We use the value 100 kilometers and to divide it by time, we directly use the value 2 hours. For hours, we use the unit H. So, when we divide 100 kilometers by 2 hours, we will get the speed as 50 kilometer per hour. As you all can see, there is a space between kilometer and hour and also -1 states it is per hour. The rate of change of distance with time. So this is another way of expressing speed when the distance is long. So now I am sure that you have a very good understanding about speed and how to calculate speeds at different time intervals as well as the mean or average speed. We will go on to the next topic, that is velocity. So as I said, velocity, we saw that this is also a vector quantity. That means it has a magnitude and a direction. Velocity also deals with the speed or how fast an object travels, but here in a certain direction. Now, for example, if you think about a railway track and two trains moving traveling on the same track. If they come with the same speed towards each other, then of course they will collide and there will be an accident. If they are going in the opposite directions, no problem. So that is why we need to consider how fast an object is traveling and in which direction it is traveling. Therefore, we use the unit or the quantity velocity, which is a vector quantity. So to calculate velocity, we consider the displacement of an object. So if I write velocity is equal to the displacement of an object in a unit time. So therefore, velocity is displacement divided by time. This is the equation. So displacement will be written in the unit meters and time will have the unit seconds. Therefore, velocity will have the unit meters per second like speed, but this will have a direction. So like how we denoted displacement, we will also have to consider the direction of velocity. If we are to define velocity, we can say velocity is the rate of change of displacement. So the rate of change of displacement or displacement in a unit time. Another way of writing it, displacement in a unit time. So now you can see this is the equation. Velocity equals displacement divided by time. That is the equation. The unit is ms minus 1 and the definition can be either written as velocity is the rate of change of displacement or displacement in a unit time. With this in mind, we will do some calculations in relation to velocity. So as you can see, for velocity calculations, we need data on time, t, symbol and s unit, and here we use displacement. The symbol is s and the unit is in meters. As we saw before, the data starts at initial time, that is 0 seconds, and the initial position 0 meters. So here you can see the table below shows the displacement of a body along a specific direction. So here they have mentioned that it is along a specific direction and each time interval is 1 second time interval. So if we are to calculate velocity, we will write velocity equals displacement over time at the end of first second. It will be displacement 3 minus 0, final minus initial, final position minus initial position, divided by time 1 second. So that is 3 meters divided by 1 second. It will be equal to 3 meter per second. Here since they say in a certain direction, we will just leave out the direction. We will just write the value. Similarly, if we calculate for the second, it will be 6 minus 3. Final position minus initial position divided by 1 second. So again 3 meters divided by 1 second. 3 meters per second. Likewise, if we keep on calculating the different velocities at different time intervals, you can see from third second 9 minus 6, that is also going to be 3. So the velocity will be 3 meters per second, and the fourth second 12 minus 9, that is also going to be 3 meters per second, and all in the same direction. So therefore, the velocity of this object has not changed. The magnitude is the same, 3 meters per second, and it is traveling in the same direction. So the direction is also same. Therefore, we will be calling this or referring this as uniform velocity or constant velocity. So here you can see when a body is moving at a constant velocity, when it is a constant velocity, another term you should remember will be uniform velocity. Neither the magnitude nor the direction of its velocity changes with time. So when both the magnitude and the direction are the same, the velocity is called uniform velocity or constant velocity. If we look at an example, a body moves along a straight line with a constant velocity of 6 meters per second for 5 seconds. What is the displacement of the body? So, as you all know, when we calculated the velocity, we divided displacement by time. So, if I write the equation again, velocity equals displacement divided by time. So, if we rearrange this equation, if you take time and multiply velocity on the other side, you will end up with displacement. So, velocity into time will give you displacement. That is only when the object is moving with constant velocity. So here you can see the velocity is 6 meters per second and the time is 5 seconds. So if I am to calculate the displacement, I use this equation. Displacement equals velocity into time. So here 6 meters per second into 5 seconds. You can see in this there is a second minus 1, second minus 1, and a second which will get cancelled off. So you will end up with the value equal So here when we calculate 6 into 5, 30, the meter unit is there, second minus 1 and second got cancelled off. So the value of displacement will be 30 meters. So as you all can see, for an object moving with a constant velocity, when you multiply velocity by time, you will end up with displacement. So that is for a body moving at a constant velocity. The displacement after a certain time interval can be obtained by multiplying the velocity by the relevant time interval. This is the same equation that we used in the previous slide. So keeping this in mind, we will look at some more examples. Again, they have given you a data table where you have time and displacement. So here you can see the displacement values are changing. So if we calculate the displacement, it is the final minus initial. So always, we have already done this. For displacement, we calculate final minus initial value. So for the first second, displacement during the first second, final is 4, initial is 0. So 4 minus 0, that will be 4 meters. Then displacement during the second second, the second final value is 7 and the initial value is 4. So this will be 3 meters. And displacement during the third second, you can see the final is 9 and the initial is 7. So here the displacement will be 2 meters. And from these values, you can see the displacement values are changing and also they are decreasing with time. In such instances, what we do is we calculate mean velocity of the object. So the mean velocity will be the total displacement of the object divided by the total time taken. So here only thing is we have to consider the direction of the object. If it moves in the same direction, you take the total displacement divided by the time. So mean velocity will be total displacement divided by the time taken. So here the total displacement is 12 meters divided by time taken is 4 seconds. So therefore the average velocity is 3 meters per second in a certain direction. Okay students, so you will have to remember, if it is uniform velocity, the displacement will be the same magnitude with time. But if it is not, then the velocity of the object is changing. And we calculate the mean velocity or the average velocity. With that in mind, we'll go to the next example. The variation of the displacement measured with respect to the starting point of a child riding a bicycle on a straight path during each 1 second time interval is shown in the table below. So if you look at this data, they have given you the displacement with time and you can see there are different regions where there is a difference in displacement. For example, if you take this region from 0 seconds to the 4th second, you can see that the displacement is changing uniformly 2, 4, 6, 8. And if you look at the values carefully, the displacement during each second is going to be 2, 2, 2, 2. But from this point, from the 4th second to the 8th second, you can see the displacement is the same value. It is at 8. The object is at the 8 meter position and it is not moving. Therefore, we call it as the object is at rest. Then if you look at the last few seconds, you can see again from 8 seconds to 10 seconds, again the displacement changes and it decreases and comes back to 0. So, since displacement has a direction, from this data you can understand that the object moved in one direction first, then it maintained rest, it did not move, and thereafter it moved backwards to its original position. So, this is the information that you can get from this data. Using that, we will do the calculation. So, the first question is, what kind of motion has the child undergone during the first 4 seconds? So, as I told you before, here you can see the displacement is the same value 2 meters in each second. So, that means the child moved with constant or uniform velocity. So, we will have to say child moved with constant velocity. Magnitude did not change, direction did not change. What is the rate of change of the displacement during the first 4 seconds? Rate of change of displacement will be displacement divided by time. Displacement divided by time. Always rate means something in a unit time. So, here if we take the total displacement within the first 4 seconds, it is 8 meters. So, 8 meters divided by 4 seconds. That will be 2 meters per second. So, from the value, the unit, you will know that we have calculated the velocity of the object. The next question, give one word to describe the rate of change of displacement. This you all know, children. What is the word? It is the velocity. Velocity is the rate of change of displacement. So, your answer will be velocity. And since we have already calculated, if they ask you for the specific instance, first 4 seconds, then of course you will have to include the word uniform. But here it is a common question. Give one word to describe rate of change of displacement. So, therefore, you can write it as velocity. What can you say about the motion of the child during the time period from 4 seconds to 8 seconds? We saw this in the previous table. From 4 seconds to 8 seconds, the displacement does not change. That means the child does not move. So, you can write the answer as child does not move. Or you can say child is at rest. So when an object or a person does not show any movement and the displacement doesn't change, we say that the object or the person is at rest. So here the child is at rest. The next question, describe the motion during the time interval from 8 seconds to 10 seconds. So if you are to understand this, initial position was here, then the child moved from here to 8 meters, and then again the child is back at 0 meter. So first this direction, then in the backward direction to the initial point. So here you will have to say the child moved in the opposite direction and reached the initial position. So here the child moved towards the opposite direction. The child moved towards the opposite direction. And find the velocity of the child during the last 2 seconds. So here if we find velocity, you all know velocity is equal to displacement over time. Displacement is calculated as final displacement minus initial displacement. Rate of change of displacement, therefore final minus initial. If we look at the values here, final is 0, initial is 8. So when we substitute those values, 0 minus 8 meters divided by time 10 minus 8 seconds. That is going to be minus 8 meters divided by 2 seconds minus 4 meters per second. So here you can see this value is a negative value, and the negative sign indicates that the child moved in the opposite direction. As you can see, first from one point to the other, then the child moved in the opposite direction. So the velocity is a negative value. I hope you understand the significance of direction in relation to velocity now.